recall that in showing that length minimizing curves of unit speed are geodesics, what we did was that we plugged in different vector fields into this first variation formula. Why were we able to plug in just any vector field? Implicitly, we have been using this lemma, which says that every vector field along an admissible curve gamma arises as a variation field of some variation of gamma. Intuitively, this means that we can deform gamma in the direction of any vector fields that we like. So let's see why this statement is true. Let gamma be an admissible curve, and let's say V is a vector field along gamma. Now we want to construct some variation, big gamma of S, T, right, such that this V, vector field V, is a variation field of this. So let's recall what this means. First of all, for this gamma ST to be a variation of this little gamma, we should have that gamma, this little gamma, is big gamma at 0, right? And so we can view this big gamma as a family of curve, gamma S, having the same endpoints as this little gamma. For this V to be the variation field of this big gamma, we need that this partial derivative is equal to V. Thus, we can think of this big gamma as the family of curves obtained by deforming our original little gamma in the direction of V. Alright, so how do we construct this family, this big gamma? Let's explain the intuition first. So, now we want to think in terms of the transverse curve. If we fix a T0 here, then each of these can be thought of as a curve in S, right? So this is a transverse curve. Now we want to construct this transverse curve as follows. So this transverse curve here, it's going to be defined to be the maximal geodesic with this initial point and the velocity vector v T0. Remember, by the existence uniqueness theorem of geodesics, we know that given an initial point P and an initial velocity v, there exists a unique maximal geodesics with this initial point and this initial velocity. We will denote that by gamma v. And note, sorry, here, unfortunately, I chose the same notation for this curve as for this maximal geodesic. They don't have any relationship. This is just a random given curve gamma, whereas gamma v means the unique maximal geodesics with initial velocity v. Now, why didn't we include p in this notation? Well, because p is already implicitly included. When we say a velocity vector, a tangent vector, that already assumed that it must lie in some tangent space. So if we know this initial velocity vector v, we know the initial point. Alright, so we want to define our variation such that the transverse curves are just these maximal geodesics with initial velocity vt0. Then from this definition, we immediately see that v must be the variation field of this variation. Why is that? Now, so first of all, what is this partial s? That's just gonna be the velocity vector field of this gamma vt, right? Remember, these gamma vt, these maximal geodesics, are transverse curves, so its variable is s. Thus, at the point 0t, this just gives us the initial velocity of this maximal geodesics, which we have assumed to be vt, just by definition of that maximal geodesic. Alright, so if we define the variation this way, then indeed v is the variation field of it. But it is not very clear from this description that this variation satisfies some of this smoothness condition. To understand that, we want to study this more general map, the exponential map. Fixing a vector v0, the exponential map of applied to SV0 is gonna give us this points on this maximal geodesics wherever both sides are defined. So our family here, if we rephrase it, it's just gonna be given by this exponential map. Now this map is extremely important, so we'll dedicate the next video to just introducing this map.